Okay, so let's look at surds. So if you don't know what a surd is, I'm going to start from the very beginning, because this is a new concept. So first, let's just want to look at what a rational and irrational number is first. Rational and irrational, because a surd actually falls under irrational numbers. So a rational number is any number that can be expressed as a fraction. As a fraction. So well, let's start with the normal numbers. So a rational numbers like -1, 1, 2, these are all rational numbers because they could be expressed as even 2/1, right? But we don't write the 1 because, as we say, the 2/1 it's a ghost one. Like we know that 10 can also be written as 10/1 when we want to times fractions together, when we can times the top and the bottom. So it's handy to know that 10 can be written as 10/1. And so these rational numbers are just fractions. And we even know that 0.3 recurring as a rational number because that's a third. And so those are our irrational numbers. Now, irrational numbers cannot be expressed as a fraction. Cannot be expressed as a fraction. And so our most famous irrational number is pi, because we know that pi is a number that does not recur. So it just carries on forever. Now, another irrational number would be e. So e is also a mathematical number that doesn't recur. And now we get to the surds. So let's now look at what a surd is. So a surd is often thought of as the opposite of a power, right? So if I say 4 squared, that's a power, right? Or an indice, 4 to the power of 2. Now, if I was to square root 4, this is now a surd. So 4 squared is 4 times 4, which is 16. But then I know that 4 square rooted is equal to 2. So I get different answers. But I also know that if I was to square root 16, I would get 4. So do you see that 4 squared is 16, whereas the square root of 16 is 4. So they are the opposite of each other. So this is actually a rational number. These are rational. So the root 16 is a rational number because it comes out to 4. But what happens if we have a not a perfect square? So 4 squared is 16. And we know 3 squared is 9. And the square root of 9 is 3. So those work fine. Those are all fall under rational. But irrational numbers is when we say the square root of, say, 17. Because if you were to put this in your calculator, it wouldn't come out at, well, actually, let's pick a number between 16 and 9. Because we know that 3, 4, and between 3 and 4 is, say, between 16 and 9 would be, say, 12. Or 13. Let's use 13 first, which is a prime number. So the square root of 13 is an irrational number. It doesn't come out nicely as a fraction because it's not a perfect square. But we know that it's going to be between 3 and 4. So it's going to be 3 point something, something, something. So you put it in your calculator, you'll get an estimation, but you won't get an exact number. It'll give you the decimals as much as it can on your calculator, but you cannot write it as a fraction. And so that's why we say that an irrational number is a surd. I'm sorry about the baby crying. We just put it to sleep. Well, we haven't put her to sleep. She's just not going to sleep. I'm just going to pause it quickly. Okay, so because root 13 is between 3 and 4, and it cannot be expressed as a fraction, it is therefore irrational. So a lot of these surds are just irrational numbers. Now, we don't just have to have a square root. It can also be a 3 here. So I just want to talk quickly about what I call ghost numbers. So when I said 10 can be expressed as 10 over 1, what we know is that there is a ghost 1 under the 10, which means that any number is just, the whole number is actually just that number over 1, but we don't write the 10 over 1. So the idea of the ghost numbers is the default, which we don't actually write. So when we looked at exponents, 10 squared is 100, but then 10 to the power of 1, there is a ghost exponent of 1 in every number where we don't have an exponent written. So if it's not a 10 squared or a 10 cubed, we know that there's a ghost 10 to the 1. So that's the 1. And then the other ghost number we can look at is when you see the square root. Actually, the ghost is, if I have, we just use the 16, there's actually a ghost 2 here. And so you see that there's a 4 squared, and so this is then root 2, so there's technically a ghost 2. Okay, now if we have, say, 3 cubed, that is 3 times 3 times 3, right? 3 times 3 is 9, times another 3 is 27. And so I could also then say that 27 to the cube root is equal to 3. So notice that because it has a 3, I know that it's a cube rooted. But if it's just a square root, we're not going to see this 2. We just have to know that it's a ghost 2. Okay, so it doesn't actually get written in. So when you see this, you must know that there's a ghost 2. Okay. Now, let's look at some properties of these surds. So one of the things we know is if I have a root 3 times a root, say, 7, these two both come out as irrational numbers, but I can still write this root 3 times root 7 as root 21. So in other words, I can times the 3 by the 7, and I can get root 21. So I can simplify this, even though these are all irrational numbers. So root 3 is irrational because it's not a perfect square. Root 7 is irrational because it's not a perfect square. And root 21 is also not irrational. Is not a perfect square, so that's also irrational. But it's simpler than just writing 3 and 7. Now I can do that again. And let's say that I was to do 4. No, not 4. Let's do 5. No, let's do 2 and 8. Okay. Now, here we have 2 times 8, which is 16, and we actually can get the answer 4. So we can get these two irrational numbers here, and they end up being a rational number when you times them together. Now let's explore this one I've just done, the root 2 and the root 8 a bit. So remember we got the answer of 4. Now let's say that we have root 2 times root 8. Now this root 8 can actually be written as root 2 times root 4, right? Because we know that 2 times 4 is 8. And so we have this idea of we split these up, like we split the 3 and the 7 to a 21. We work backwards from this 8, and we go 8, well, that's 2 times 4, and you split it up. And what we end up having is, well, what's root 2 times root 2? Well, that's root 4 times root 4. And we know we can actually get the square root of 4, which is 2. And the square root of 4, which is 2, and we get 4. And we got that same thing here, right? Root 2 times root 8 gives us root 16, which is 4. So we can see how these numbers work out. And so we can prove these rules just by using various numbers that we put in. Okay, so that's a surd. A surd is the opposite of an exponent, and it can be handy in solving equations, and that's what we're going to do now. So if we look at x squared equals 9, what we can do is we can square root the x squared and the 9. So remember, when we're dealing with equations, if you do what you do to one side, you do to the other, because then there's a nice symmetry, right? And I know the square root of 9 is 3, and the square root of x squared. So what happens is, because these are the opposite of each other, because you have a square root and a squared, these things cancel out just to leave me with the x. So in other words, these things cancel out. So a squared can be canceled out by a square root because they're the same thing. Now, we just have to do one more thing to make this answer fully correct. When I times 3 by 3, I get 9. So I know that that's right, because x squared is technically x times x. And so 3 times 3 would be 9. But what happens when I do minus 3 times minus 3? Well, I know that a minus times a minus from topic 1 with our integers, which I'll put a link into the description. With our integers, we count the number of negatives, and if it's even, it comes back to a positive, and so we get 9. So in other words, minus 3 times minus 3 would also give us a 9. So x could have been minus 3 as well. And so whenever we square root a number in an equation, we have a plus or minus 3. So don't forget, and it's something to remember, always bear in mind that when we square root this 9, our answer could be plus or minus from what we've seen here. Now, that was a perfect square. Let's deal with this again. We would square root b and square root. So because we have a square, this would get rid of the x because we want to solve for x. And so we get a surd here. And we cannot do, it's not a perfect square, but it has to be plus or minus because of what we said earlier with the 3. And so we end up getting a surd helps us with solving an equation where we don't have a perfect square. And when we're solving an x squared, we can get a plus or minus root 10. Okay. And we just have to leave this as it is. With this one, it's going to be slightly different because we do have an x equals, so we square root the square to get rid of the square. And we say plus or minus 18. But now what you'll notice is in your calculator, if you square root 18, it'll give you a different answer. It'll give you 2 root 3. Why? Well, this plus or minus 18 can be written as 2 times 9. Or we can write it as just root 2 times root 9. And so your calculator says, well, I can get the square root of root 9. The square root of 9 is 3. And so it'll end up giving you the answer of this 9 will actually, the square root of 9 will actually be given to you as 3 root 2. So this is quite a confusing concept. I'm not going to go into too much detail, but when you see this, just know that your calculator is breaking this 18 up into numbers that can be square rooted. I'll just do one more example. Let's say we had something like what's 16? Let's try 32. Okay, so we know that 32 is actually 16 times 2. And so what your calculator does is it says, well, I know the square root of 16, that's 4. And I cannot get the square root of 2, and so it'll give you the answer of root 32 as 4 root 2. Okay, and that's sort of simplifying these surds by using the fact that root 3, say, times root 7, as we did earlier, we actually know it's just root 21. So these surds, we can multiply and divide them, and we'll be doing some more in E, F, G, and H. Last one, we square root. The last one is a special case. We need to square root both sides to get rid of the x, and then we get plus or minus. But now, put -9 into your calculator, you will get a non-real number. You will get a math error. And so this is undefined. No answer. And so we can't actually say, we say x is undefined. Because we can never get a square to be a negative number. Because let's say I have -3 times -3. Well, that'll just become 9. And 3 times 3 will become 9. So I can never get this to be a negative. Because if it's a negative or positive, it's still going to come out as a positive. So I cannot get a negative when I square a number. So this is impossible. And so x is undefined, or x is no solution, or I can say no solution. Now we do have a way when we do complex numbers in AS levels of dealing with the square root of a negative. But for now, just know that for now we just say it's no solution. Okay, so now let's look at this concept of the breaking up of the number. So root 9 times root 4. Well, we know that the square root of 9 is 3 and the square root of 4 is 2, and we get the answer of 6. Now, 9 times 4 is 36, and the square root of 36 is 6. So this again illustrates that you can take the 9 and the 4 and you can write it as root 36. And so just remember that if you have two surds multiplied by each other, you can times the inside, and that'll give us our final solution. So if you were to try and get negative root 2, you cannot get this, or root 18. These are irrational. But if I get it to 2 times 18 of being 36, well, that's the same answer as I had before, which is 6. And another way of doing it, so we're just exploring numbers here. 18 we can write as 2 times 9. Right, so root 2 times root 9. And again, we see, well, root 2 times root 2, when you times two numbers that are surds together and they're the same, the surds actually go away, because technically 2 times 4, 2 times 2 is 4, and the square root of 4 is 2. So root 2 times root 2 actually just gives us 2. And root 9, square root of 9 is 3. And so, yeah, so we get to 6. There's all these different ways of going forwards and backwards with numbers. And so here we can say, well, the square root of 36 is 6, and the square root of 4 is 2, and 6 divided by 2 is 3. We could also say 36 divided by 4, and that's 9, and the square root of 9 is 3. Okay. So I don't want to confuse you and say that you need to do both methods. Just illustrating the idea that you can times in the two surds together. And so you can get 2, and so particularly with F, where you have 2 and 18, which don't work nicely. But when you times 2 by 18, you get 36, and that is much easier to work with because 36 is a perfect square. So when you're dealing with surds, you need to know your perfect square numbers, which we'll just we'll do just now. Root 18 and root 2 are both awkward to deal with, but we can, 18 divided by 2 is 9, and the square root of 9 is 3. Okay, so if you can't do the surd, if you can't get the square root of 18 and the square root of 2, but it's dividing, you can divide 18 by 2 because they're both square rooted, and get 18, and this you can actually 9, and you can actually deal with that. So it's very important to actually be able to look at numbers when you're dealing with surds, and remember about the perfect squares. So what are our perfect squares? Well, 1 times 1 is 1, so that's your first perfect square. 2 times 2 is 4. 3 times 3 is 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. 7 times 7 is 49. 8 times 8 is 64. And 9 times 9 is 81. And then 10 times 10 is 100. And so these numbers here, start to memorize those, because then if you get a question like x squared equals, say, 81, you can see, you can remember, I know that 81 is 9 times.
Nick, sorry to interrupt, but I have to go. I did message you, but you didn't. Sorry, I don't want to interrupt the recording. Sorry.
Okay, I'm actually done now. So yeah, we'll finish there, and yeah, we'll see you next time for topic 4.